The cosmologist Carl Sagan famously observed that human beings are made of star stuff. When you look at the chemical makeup of the human body, the calcium in our bones, the oxygen in our lungs, and the iron in our blood all had to originate somewhere in the cosmos. But the universe did not start out with these materials. In the minutes following the Big Bang, the cosmos contained only the simplest, lightest elements, hydrogen and a small amount of helium. To forge the rest of the periodic table, the universe required a manufacturing engine capable of generating extreme heat and immense pressure. Our physical existence depends directly on a cosmic mechanism with enough power to fuse those simple early elements into the complex biological building blocks of life. We find that engine deep inside the core of a massive star. For billions of years, this environment serves as the battleground for a continuous, violent physical conflict. This diagram illustrates a delicate balance known as hydrostatic equilibrium. The blue arrows represent gravity, constantly trying to crush the star's mass inward, while the red arrows show the outward push of nuclear fusion fighting back. Under immense pressure, 4 hydrogen protons smash together, fusing into a single helium nucleus. Notice the seesaw below. The new helium nucleus weighs slightly less than the original protons. Following Einstein's equation, E equals mc squared, that missing mass converts entirely into pure energy. This continuous conversion of physical mass into radiating energy provides the sole outward pressure, keeping the massive star from collapsing entirely under its own gravity. Eventually, this balance breaks. After millions of years, the core burns through its supply of hydrogen. The fusion engine stops, and gravity instantly begins to win, crushing the core inward. But this violent compression causes the internal temperature to spike. The core reaches a new threshold of heat and density, forcing the newly created helium atoms to fuse into carbon. As the star ignites these heavier elements, the outer atmosphere swells, turning the star into a red supergiant. Inside, the core develops distinct stratified layers of different elements, resembling an onion. This forces the star into an exponentially accelerating timeline. To maintain the pressure needed to hold up its immense weight, a star 25 times the mass of our Sun will burn through its entire supply of carbon in just 600 years. The collapse resumes, temperatures rise further, and the core begins fusing neon. That supply is exhausted in exactly 1 year. Next, it burns through its oxygen layer in a mere 6 months. Finally, the core is left to fuse silicon. In just one single day, that silicon is forged into iron. This frantic, rapidly shrinking timeline reveals the reality of the situation. The star is burning through its fuel at an unsustainable rate, fighting a desperate and inevitably losing battle against the relentless crush of gravity. The fusion cycle stops permanently, with the creation of a solid iron core at the absolute center of the star. Iron possesses unique physics. It is the most stably bound isotope in the universe. Because of this, trying to fuse iron atoms together actually requires energy to be absorbed, rather than releasing it outward. The immediate consequence is catastrophic. The star's internal energy engine shuts down instantly, and the outward pressure fighting gravity drops to 0. By forging iron, the star seals its own fate. With nuclear fusion completely dead, the billion-year war is over. Gravity wins. The defeat happens in a fraction of a second. Unimpeded by any outward force, the massive iron core collapses in freefall, reaching 23% the speed of light. As millions of tons of matter crush inward, the extreme pressure physically forces electrons and protons to merge. This process, called neutronization, converts the entire core into a single, incredibly dense ball of neutrons. The collapse only halts when the core reaches supranuclear density. At this point, the core becomes so tightly packed that the physical laws of nature prevent it from compressing any further. It becomes an impenetrable physical wall. The rest of the star is still falling inward at unimaginable speeds. That infalling material slams into the solid neutron wall, bounces off and rides a massive wave of newly created neutrino particles surging outward. This rebounding shockwave is a core collapse supernova. The sheer kinetic energy physically rips the dead star apart from the inside out. The supernova acts as a final, high-energy forge. Its shockwave generates temperatures and a rapid neutron capture environment impossible to achieve inside a stable, living star. In the brief, chaotic seconds of this detonation, atoms collide and capture neutrons fast enough to synthesize the heaviest elements in the universe, including gold, platinum, and uranium. Long after the light fades, the aftermath remains visible. This X-ray image shows Cassiopeia A, a massive, expanding cloud of stellar debris known as a supernova remnant. These remnants serve a vital cosmic function. As clouds like the Crab Nebula expand, they scatter their newly synthesized heavy elements across interstellar space, eventually seeding the gas clouds that form subsequent generations of planets and ecosystems. The iron carrying oxygen through our blood and the calcium providing structure to our bones were forged in these extreme environments. We are composed of the scattered shrapnel of a dying star's lost war against gravity. A standoff that lasted for millions of years is lost in less than a second. The star's outer layers plummet into the void left by the core, strike the dense center, and rebound. This creates a shockwave that erupts as a core collapse supernova, ejecting most of the star's mass into space. The remaining core now faces a specific physical limit known as the Tolman-Oppenheimer-Volkoff, or TOV, limit. As the core compresses, it crushes protons and electrons into neutrons. These neutrons resist being packed any tighter, creating a force called neutron degeneracy pressure. This quantum effect serves as the final barrier against gravity. If the core's mass is below roughly 2 solar masses, this quantum pressure holds the core stable. It leaves behind a city-sized sphere of pure neutrons, a neutron star. In these objects, the laws of quantum mechanics provide the final resistance against gravity. If the core exceeds roughly 3 solar masses, even quantum resistance fails. At these densities, general relativity introduces a new variable. Einstein's equations show that all forms of energy, including internal pressure, have a gravitational effect. As the core tries to generate more outward pressure to stop the collapse, the energy of that pressure gains its own gravitational weight. This extra weight adds to the force pulling inward, actively helping gravity crush the star. This leads to the Bookdahl limit. Past this point, any increase in outward pressure actually increases the total gravity of the core, making a total collapse into a black hole mathematically certain. For the most massive stars, the physical force intended to provide support becomes the primary cause of its destruction. Gravity continues to compress the mass past a volume defined as the Schwarzschild radius. This radius marks the event horizon. At this boundary, the gravitational pull is so intense that the speed required to escape it is higher than the speed of light. Since nothing can ever travel faster than light, the collapsed core is permanently removed from the observable universe. The result is a localized, permanent distortion of spacetime that no longer emits or reflects light. Because black holes do not allow light to escape, astronomers must rely on indirect evidence to find them. One method involves tracking the motion of visible stars at the center of the Milky Way. This data shows stars orbiting a central point with massive gravity but no visible light, allowing us to calculate the invisible object's mass. Astronomers also detect high-energy X-ray emissions from material near a black hole. As gas and debris fall toward the event horizon, they are stretched and heated by gravity, releasing radiation that telescopes can identify. These regions are the physical consequence of gravity's absolute victory over the forces of matter.